Hello everyone, myself Dr. Arun Babu. Currently you are at Characterization Facility of Center for Nanoscience and Engineering, and we will be demonstrating how to use an FTIR facility and how to interpret the data. So this is whatever you are seeing here, this is the FTIR spectrometer, and FTIR stands for Fourier Transform Infrared Spectroscopy. As the name suggests, it is an infrared spectroscopy which actually deals with the vibrational spectra of a molecule. Now, the first question is why we need to study an FTIR? What is the importance of an FTIR? So, the importance of FTIR comes when you have an unknown sample. If you want to study the composition of an unknown sample, you can actually use an FTIR. It will tell you what is the different functional group present in the sample.
Before explaining more about the FTIR spectroscopy, let us go through a few of the basics here. We all know what is an electromagnetic spectrum. An electromagnetic spectrum is nothing but it's an arrangement of electromagnetic waves in increase or in decrease in the wavelength. So here we can see our electromagnetic spectrum is start with a lower wavelength and it increases as we go from left to right. Since the frequency and the energy both are inversely proportional to the wavelength, as the wavelength increases, the frequency and the energy decreases. So he can say like in this electromagnetic spectrum, as we grow from left to right, the frequency and the energy is decreasing. At the same time, the wavelength is increasing. Now, in FTIR spectroscopy, we are mainly interested in the IR region, which is normally in the range from 700 nanometer to 1 centimeter in wavelength. In FTIR, we use wave number instead of wavelength, which is nothing but it's the inverse of the wavelength. Now, the most important question, why only IR region? It is because FTIR is a vibration spectroscopy and the molecular vibration transition is always coming in this infrared region. So what we do in FTIR is like we send a broadband of light through the sample and we will analyze the light which is coming out of the sample. So broadband of light is nothing but it has a large number of wavelength. So we can say for an example we can say like 2500 nanometer to 25,000 nanometer. In the terms of wavelength or in terms of wave number, it is correspond to 400 centimeter inverse to 4000 centimeter inverse. So this broadband of light we pass through the sample and at the output we will check what all the frequencies are absorbed by this sample. So from that we will be able to get a spectrum or an FTIR spectrum of this particular sample. This is a typical FTIR spectrum. The x-axis here is the wave number and y-axis is the percentage transmittance. So as I told, wave number is nothing but it's the inverse of wavelength or it is proportional to the energy. So 4000 centimeter inverse correspond to one particular energy, 3000 centimeter inverse correspond to one particular energy. Like that, entire point in this x-axis is representation of a particular energies. If there were 100 photons at 400 centimeter inverse, how many photons are coming out of the sample? If you send these 100 photons through the samples, then how many photons are coming out of the sample is given by this y-axis. So that is the percentage transmittance. So you can see here in this particular graph at 4000 inverse, we are getting a transmittance of 100%. That means if there were 100 photons in the input beam and once it passes through the sample, none of the photon is getting absorbed and it is reaching the output. Now, if you consider till 3200, the entire transmittance is 100%. That means none of the photons in this range from 4000 to 3200, none of the photon is getting absorbed by the sample. Now, again if you see from the region around 2600 to 2000, again its the transmission is 100%. That means if there were 100 photons for each individual frequencies in this region, none of those frequencies or none of those energies are absorbed by the sample. At the same time, when you see this 3000 centimeter inverse region, you can see there are 1, 2, 3, 4. 4 strong absorption is happening in this region. So at around 3100, we get a transmission of only 40%. That means 60% of the photons are absorbed by the sample at this particular frequency. Now again, around 2900, you can see three particular frequencies are almost completely absorbed by the sample. Now again, if you go some other points, you can see there are different absorption. And one thing here is common, it is not a continuous absorption. The absorption, whatever the FTIR shows, it is actually quantized. It's actually appearing at different frequencies, but that frequency is definite frequency. It's like it is not changing in time. This is how a typical FTIR spectra will look like. You have wave number in the x-axis and percentage transmittance in the y-axis. So wave number is nothing but it's the inverse of wavelength, or you can say like each point in this x-axis represent a wavelength or a frequency or an energy. So 4000 centimeter inverse means there is a particular energy correspond to that. 3000 centimeter inverse means there is a particular energy correspond to that. So if you see this region from 4000 to around 3200, the transmittance it shows 100%. That means if there are 100 photons in each of these wavelength or in each of these wave number, none of these photons are absorbed by the sample. Whatever was there, if there are 100 number of photons in the incident beam, once it passes through the sample, ended 100 number of photons are reaching the detector. There is no absorption of any photon in the range from 4000 to 3200. Now, if you see the region between 2800 to 3200, 3200 to 2800, there are 4 absorption bands. So 1, 2, 3 and 4. There are 4 absorption bands happening between 3200 to 2800. Now again, if you come in this region from 2000 to 2600, the transmission is 100%. None of the photons with the energy in this range is getting absorbed by the sample. Further, if you go below 2000, you can see there are multiple absorptions happening at discrete frequencies. This is how an FTIR spectrum will look like. Now, what we do is, once we get the spectrum, we will see at what all frequencies this absorption is happening. And from that, we actually interpret the FTIR graph. Now, let us see what is the reason we get different absorption at different frequencies. To understand this, let us consider a diatomic molecule. Once any two elements combine to form a molecule, the so-called bond, it will be always vibrating. So this vibration frequency of any diatomic molecule is given by the equation 1 by 2 pi root f by nu, where f is the force constant and nu is the reduced mass. So force constant here is nothing but the bond strength. So once a bond is formed, the bond strength will be constant and the reduced mass, that also will be constant. So for a particular diatomic molecule, it can vibrate only at one particular frequency given by the equation 1 by 2 pi root f by nu. So until any of these parameter changes, it cannot vibrate at any other frequencies. So if you consider a carbon-hydrogen bond, since the mass and the bond strength both are constant after the bond is formed, it can vibrate only at a frequency in and around 3000 centimeter inverse. Now, if you are changing the hydrogen with a deuterium, so deuterium is nothing but it has a higher mass compared to hydrogen. So as the mass increases in this particular bond and the mass coming in the denominator, we can see there is a decrease in the vibration frequency as you change carbon-hydrogen bond to carbon-deuterium. As you increase as you change the element, a lighter element with a heavier element, you can actually see there is a decrease as we increase the total mass of the system. Now, coming on to the bond strength. So a single bond will have a lesser bond strength compared to a double bond and to a triple bond. And similarly, we can see here for a single bond, the vibration frequency, it is, you can say like it will be coming between 1500 to 1000 centimeter inverse. As the bond strength increases to double bond, the frequency increases here. So the double bond normally comes in the region around 2000 to 1500 centimeter inverse, and the triple bond, which has the higher bond strength, which will be coming around 3000 to 2000 centimeter inverse. So this is what happens once you change the bond strength or the mass of a diatomic molecule. Until any of these things are changed, it can vibrate only at one particular frequency. Now, what happens when a diatomic molecule vibrates? So if you consider a carbon hydrogen bond, so we always know that one side carbon, one side hydrogen, so there will be always a charge separation. So equal and opposite charge separated by a distance, you will get a dipole there. So when it starts vibrating, you can actually consider it as a vibrating dipole. So this dipole is vibrating at one particular frequency, and when a photon of the same frequency falls on this vibrating dipole, this dipole can absorb that particular frequency. So if you have a particular bond which is vibrating at a frequency x, and the light which has a frequency x falls on this particular vibrating dipole, the dipole can absorb that particular frequency. It cannot absorb x plus 1 or x minus 1. It can absorb only the particular frequency at which this dipole is vibrating. Consider I have a broadband of light from 4000 centimeter inverse till 400 centimeter inverse. So, and I have a sample, or like I have a bond which is vibrating at 3000 centimeter inverse. So I am sending the broadband of light through this bond, and I am checking what is the output I am getting. So what happens is, like, since the bond is vibrating at 3000 centimeter inverse, the light which is at the 3000 centimeter inverse frequency, that this bond will absorb. So rest of the frequencies, it will reach the detector without any absorption. So you can say from 4000 centimeter inverse till 3001 centimeter inverse, and similarly from 2999 centimeter inverse till 400 centimeter inverse, all will be reaching the detector except one frequency, that is 3000 centimeter inverse, which is the vibrating frequency of the bond. So this is how we will be getting an FTIR spectrum. Therefore, whenever we see a FTIR spectrum like this, it says that there is, just consider the region from 4000 to 2000 only. We are not talking about the rest of the region right now. We just consider from 4000 to 2000 only. So in this 4000 to 2000 region, we can see there is only 4 absorption happening, and those are around 3000 centimeter inverse. That means there are 4 bonds which is actually vibrating in a frequency range between 4000 to 2000. So what are those bonds? That is what we will interpret in an FTIR spectrum. So since we know what is the mass and we know what is the bond strength, we can actually calculate these things well before we do an FTIR, and we can prepare a tabular column. And in the FTIR spectrum, we can mark down at what all frequencies these absorptions are happening. So once you compare whatever you are getting in FTIR spectrum with the standard table, we will be able to understand what are the functional group present in the particular sample. That is what we normally do here. So if you consider this particular graph, we can see there are 3 absorptions happening near that 3000 region. So these 3 absorptions are mainly due to carbon and hydrogen bond. So this is CH bond. So as I was saying, CH can vibrate only at one particular frequency as long as the bond strength and the mass doesn't change. So at the same time, we can see there are 3 absorptions happening here. This is because the CH bond can exist in 3 different hybridization. So it can be sp hybridization, it can be sp2 hybridization, it can be sp3 hybridization. Depends on what hybridization it has, the bond strength will be different. Even though the mass, carbon hydrogen mass, is not changed, since the hybridization is different, we will have a different bond strength. So as the bond strength change, we can see there are 3 different absorption for carbon hydrogen. So if all three were same hybridization, we should get only one absorption peak. But carbon hydrogen can exist in different hybridization. So three hybridization is possible for carbon hydrogen bond. We are getting three absorption band. So this tells you that if there is any small change in the bond strength or the mass, we can actually identify that in the FTIR spectroscopy. So you will be able to identify isotopes in an FTIR spectroscopy. Whenever do you do an FTIR analysis, the first thing you need to do is taking a background. A background is nothing but it is the measurement of the inherent property of the instrument. So at this point, you will record a spectrum without keeping your samples. So that will tell you what is the maximum thing or what is the maximum photons at each wavelength the instrument can expect. So the next time you keep your sample and you will compare the output with the previous measurement. So initially you can see here. So this is my background. So the background involved what is the response of my source, what is the response of my detector, what is the response of the optics, whatever is present in the beam path. So you can see at 4000 centimeter inverse, the number of photons from the detector or the number of photons total present, it's less compared to around 1500 centimeter inverse. Okay, so this is the total profile of the source and detector and the entire optics when you take a background. So background nothing but you are just without the sample, you are just taking a spectrum. So here you can see there are already absorption band present. So this band is actually due to carbon dioxide and these bands are due to the moisture bands. So even before you keep a sample, you already have some absorption present. Now, second time you keep the sample and you record the spectrum. So initially we record the background. After recording the background, we keep the sample and we record the spectrum. So in this spectrum, so this is the spectrum what you are getting when you keep the sample and you record the spectrum. But in the spectrum, you can see there are already absorption band from the background. So we don't need this absorption band which is actually coming from the background. So we need to remove it. So to remove it, what we do is we take a ratio between these two, between the background and the sample. You take a ratio so that whatever was previously present, all those will be removed. And finally, you will get a spectrum which is background corrected. This is what an FTIR does. Initially, you take a background. Next time you keep the sample and record the spectrum. The FTIR instrument itself will do this ratio. So we don't have to do anything separate. So once you took the background, next time when you record the spectrum, whatever is the output, this instrument, it will take a ratio between the background and it will give you the final spectrum so that whatever was the peak present in the background, that will be removed and you will get the spectrum only from your sample. Now let us see what is a background. A background means anything other than your sample which is coming in the beam path. That is called your background. So if you have a thin film on a substrate, so the substrate comes in the background. So initial when you are doing the background, you keep the substrate, only the substrate in the beam path and you will do the background. Now next time when you want to measure the sample spectrum, you will keep the sample plus substrate in the beam path and when you do the analysis, whatever was the contribution from the substrate, it will be removed and you will get only the sample spectrum. Let us discuss few of the sampling methods here. So depends on what kind of sample. You have to choose different modes in an FTIR. So if you have a sample which is on a transparent substrate, you can actually place the sample directly in the beam path and get the data. So that is called transmission mode. So you are keeping the sample directly in the beam path. So the light will be passing through your sample and reaching the detector and you are recording the spectrum. So this is the transmission mode. Now, what if your sample is having a substrate which is not transparent? So light may pass through your sample, but it will not pass through the substrate. So in this case, you won't be able to keep the sample directly in the beam path. So in that particular case, either you have to do a specular reflectance. It's nothing but, okay, your sample you keep at one position and the beam will be reflecting from your thin film. So you can use spectral reflectance if you have a absorbing substrate. Another method is called attenuated total reflectance, ATR. In ATR also you can use thin films. So the thin film will be touching the ATR crystal and the analysis will be happening like that. Now, what if you have a powder sample? So we cannot just sprinkle the powder sample in the beam path and get the FTR spectrum. So what we do is we normally mix potassium bromide and we will make a pellet out of this powder sample. And this pellet can be placed in the beam path and we can measure FTIR in the transmission mode itself. If you don't have a metal oxide in your powder sample, you can use ATR crystal, ATR method to do this analysis. The problem with metal oxide is like normally an ATR range is restricted with that ATR crystal. So if it is a diamond crystal, the ATR range will be maximum 4000 to 650 centimeter inverse. And all the metal oxide will have a peak below the 650 centimeter inverse. So ATR mode cannot record the absorption peaks of a metal oxide. Therefore, we won't be able to use ATR mode for a sample which is having a metal oxide. So if the sample contains metal oxide, we have to make a pellet out of this powder sample and you have to use in the transmission mode. Similarly, if you have a liquid sample, we just need to put a drop on top of the ATR crystal and we can get a very good FTIR spectrum using ATR mode. So like this, depends on what kind of samples you have. You have to choose one or the other mode. Okay. Till now, we were discussing about how to get an FTIR spectra. Now let us see how do we interpret this spectra. So an FTIR spectra from 4000 to 400 centimeter inverse, we can divide into two regions. So one is functional group region and second one is fingerprint region. So 4000 to 1500 centimeter inverse, that region is called functional group region, where all the functional group like carbon, hydrogen, carbon, oxygen, or oxygen, hydrogen, something like that will appear. Now, the region from 1500 to 400 is called fingerprint region, where the vibration from the entire structure that will be appearing in the fingerprint region. So if you consider ethanol and methanol, both are having same functional groups. So in this 4000 to 1500 region, you will be seeing similar or the same absorption peak. Now, the functional group region, for the fingerprint region, will have a different set of spectrum, which is because there is an extra carbon hydrogen bonds in the entire structure. So as the vibration from the total or the skeleton, it is different for ethanol and methanol. So we will find a different set of vibration absorption peaks in the fingerprint region for ethanol and the methanol. But both of these has the same functional group. The functional group region will have the same set of absorption peaks. So normally, to interpret a spectrum, what we do is we normally see what are the functional groups or what are the absorption peak in the functional group region, and from there we will see what are the absorption present in the fingerprint region, and from there you will be having an idea about what is that particular composition. Now let us see the absorption spectra of few of the functional group. So as I told, the initial thing in FTIR is to take a background. So the background normally look like this. So you have a absorption from moisture as well as the carbon dioxide. So after the background, you do the analysis of the sample. So you get a spectrum like this. So this is an axene spectra. So where you can see the carbon hydrogen. So carbon hydrogen bond or the absorption band will be coming in this region from 3000 to 2800 region. So if you have an OH in the sample, so that OH will be coming in around 3300 to 3600 centimeter inverse. So this is the region where you find an OH absorption. And OH absorption is not sharp like CH, it is actually a broad absorption. Now coming on to triple bonds like carbon triple bond, nitrogen triple bond, that will be coming around this 2200 region. So if your sample has nitrogen and hydrogen bond, so NH bond normally comes in the region 3400 centimeter inverse. So depends on what functional group you are having. the position of the functional group will be different. So since we already know what is the bond strength as well as what is the mass of these elements, we can actually calculate those and put it on a table, and later you do an FTR and see what are the absorption band present and compare the frequency of this absorption with the tabular column we are already having it. We can identify what are the chemical composition of the samples. This was the theory and how to do the spectral interpretation of an FTIR spectroscopy. Now let us move on to the hands-on demo on how to prepare the sample and how to do the analysis, how to do the hands-on using an FTIR spectroscopy.
Now, let's have a discussion about how to do an FTIR. So presently, the FTIR spectrometer is set to the transmission mode. So the IR light starts from here, it passes through the chamber and it will reach the detector. So any sample which I am keeping in the beam path can be analyzed using this mode. So initially, before starting an FTIR measurement, the first thing you need to do is to take a background. So background is nothing but you don't keep your sample. Without keeping the sample, you take a measurement and tell the instrument what is the maximum it can expect. For that, there is a button on the software. So the background in FTIR can be acquired by clicking on this button written as background. Once we press the button, we can actually see the instrument start acquiring the data, and this data doesn't have any information from the sample. This is only the information about the source and the detector. So once this background is recorded, we can place the sample in the beam path. We can place the sample in the beam path and change the sample name and scan it. So this time we can see the spectrum is from the sample. So this is an absorption spectra from a polystyrene sample, and you can see there are multiple absorption bands present here. So this region up to 1500, this region is actually known as functional group region, and from 1500 to 400, this is known as fingerprint region. So whichever is the functional group, like carbon, hydrogen, carbon, oxygen, that functional group will be coming in this region, and the total vibration to the entire structure will be coming in this region. So if you have a thin film sample, so normally thin film will be on a substrate. So in that case, whenever you are taking the background, so you need to keep the substrate in the background and record the data, record the background. Otherwise, whenever you are just doing the background in the air, so next time when you keep the sample and the background, sorry, sample and the substrate, it will record the spectrum of both substrate as well as the sample. So to avoid that one, we need to keep the substrate initially in the background, and next time you keep the sample plus substrate, so that whenever the scan happens, it will remove the background part itself. When you have powder sample and you want to do FTIR, since you cannot just sprinkle this sample in the beam path, we need to make a pellet out of it. So normally we will mix with potassium bromide, and using a pellet die and a pellet press, we will make a pellet in this form, and this pellet can be placed in the holder. This can be placed in the holder and we can do the analysis. So once the data is recorded, we can do the post-processing like background correction to get a better looking graph. So background correction will give you a better looking graph in FTIR. Now, what if you have a liquid sample? So liquid sample, you can do FTIR in two different methods. One is using a cuvette. The second one is using an ATR. So normally, right now we have set the instrument to normal transmission mode. So I will change that to the ATR mode. So this is the ATR accessory. So here the light will be coming from this part of the instrument and it will reflect on top of the ATR crystal and go back to the detector. So here what we do is, if you have a liquid sample, we need to place the sample on top of this ATR crystal. Okay. So initially, as I told, in any mode of FTIR, first thing you need to take is the background. So once I install the ATR module, initially I have to take the background. So once the background part is done, we can put the sample on top of the ATR crystal and start the analysis. So this is the FTIR spectra of an isopropyl alcohol. So you can see different peaks from OH and CH are already appeared here. Okay. So ATR you can use not only for the liquid sample, you can use powder as well. So if you have a powder sample for ATR, you just need to put the sample on top of the ATR crystal, tight this one up and scan in the software. So here you don't have to worry about spending a long time to prepare the pellets. But one drawback of ATR is like ATR range will not go up to 400 centimeter inverse. So whenever you have any metal oxides, you won't be able to use ATR because metal oxide absorption peak will be coming between 500 to 400 region. So that region won't be covered in an ATR. So in that case, you have to do a pellet and you have to record the spectrum in the direct transmission mode. So as we discussed, you can see that FTIR can be used to identify an unknown composition. I hope this session was helpful for you. Thank you.